What I'd like to do in this short video is run through section 1.1 of our textbook, not with the purpose of going through section 1.1 because you can read that, but with the purpose of learning how to use our TI-89 calculator. So when we start in section 1.1, it talks about functions. You can read the definition and so on for yourself. And then we get down here to quick check 1, where a function is defined and then we've evaluated at certain inputs. How would we do that on our calculator? Well, when you turn on your TI-89, you get to the application screen, and we'd like to go to the home screen, which happens to be highlighted, so we'll press enter. If it wouldn't be highlighted, you could use the arrow keys to highlight home and press enter. So how do we define a function? This is something we'll be doing a great deal. So how do we define a function is under the F4 other menu. So you'll press F4. It's option 1, define, so we'll press 1. We'll give the function the name, f. So f is located above this key here. So alpha f evaluated at x is equal to x squared minus 2x. So x squared minus 2x. Enter. Now that the function is defined, we'd like to evaluate the function at -1, so let's do that. F evaluated at, and be careful, this is the key for negative numbers, that's the subtraction key. So -1, close the parentheses, enter. So F evaluated at -1 is 3. Now we want F evaluated at x squared, so let's do that. F evaluated at x squared. Enter. F evaluated at t. Well, that shouldn't be too difficult. Enter. And finally, F evaluated at p minus 1. So F evaluated. P is located here above the store key. So alpha p minus 1. Close your parentheses and enter. So let's check our calculator against the textbook. F evaluated at -1 is 3. We got that. F evaluated at x squared, x to the 4th minus 2x squared. We got that. F evaluated at t, obviously is t squared minus 2t. We got that. F evaluated at p minus 1, p squared minus 4p plus 3. Now we didn't get that. Hopefully you can recognize that they're equivalent. But how would we make our calculator get the same answer? Well, that's an algebra problem. We would like this multiplied out. So we would like to expand that, and that's under the algebra menu, F2. Option 3, expand. So we would like to expand F evaluated at p minus 1. That's closing the parentheses for the function. That's closing the parentheses for the expand command. And you'll see we get the same answer. Okay. Next, we talk about the vertical line test. In example 1, they actually give you the graph, so we don't need our calculator. So let's move ahead to example 2, where we are supposed to graph these with a graphing utility using the given window. So luckily we have a graphing utility. So we'd like to graph the function f of x is x squared plus 1. And the viewing window, we want x to run from -3 to 3 and y to run from -1 to 5. So how will we do that? Well, the graphing keys are these yellow keys up here, y equals window and graph. So to get those, we need the diamond. So we need to define our function first. So diamond y equals. You can plot many things at once. We only want to plot one, so y1 equals x squared plus 1. And enter. Now we'd like to graph that in a particular window, so we will use the window button here. So diamond window. This is the default window from -10 to 10, but we would like the x to run from -3 to 3, so we'll change that. Use the down arrow to 3. The next one, x scale, that just tells you the value for each tick mark. We'll leave that at 1. Y we want to run from -1 to 5. And again, we'll leave the scale at 1. And now we want to graph it. So that's above the F3. And there is our graph. So let's check that. You'll notice the graph in the book is much nicer. One of the things you'll notice on our graph is that our graph doesn't seem to go up as steeply. In the book, you'll notice that the tick marks are equally spaced and ours are not. Notice that the tick marks don't seem to be equally spaced in the X and Y direction. There's 1 in the Y direction, there's 1 in the X. So the scale in the X and Y direction doesn't seem to be the same. If we'd like them to be the same, we will change the window on that. We can do that with the F2 zoom command, F2, and that is called zoom square, option 5. That evens out the tick marks. So now you'll notice that a length of 1 horizontally and a length of 1 vertically look the same. So now our graph looks closer to the graph in the textbook. Okay, let's try the second one. So we want to graph the square root of the quantity 4 minus t squared. Okay, well let's enter our function. So I don't want to graph more than one function at a time, so I'll clear the old function. Now recall from algebra that the square root is actually the same as the 1/2 power, so let's use that knowledge. So y1 is 4 minus. Now you'll notice that the TI-89 only wants to graph with inputs being x. So instead of typing 4 minus t squared, we'll simply type 4 minus x squared. That won't affect the graph. Close the parentheses and raise that to the 1/2 power. Notice I have parentheses around the 1/2. And enter. You could have also used the square root button there, located there above the x, or the multiplication symbol, I should say. So let's graph that also, and when we see only one graph, we'll know they're exactly the same. So let's do that one. Okay, so second square root 4 minus x squared, and enter. Now the window we want, x run from -3 to 3, that's the same as before. Y runs from -1 to 3. So let's change our window. So we want x to run from -3 to 3. We'll keep the scale at 1. And we want y to run from -1 to 3. And then graph. This is above F3. And there's the graph. You'll notice because of the screen resolution, it doesn't come all the way down here to touch. In reality, the real graph does, but that's just a function of screen resolution. So we'll go down and check our answer. It looks like a semicircle. But again, because of the resolution and because of the way this graphs, again, notice the x input and the y inputs. 1 is not the same space. Again, if you'd like to, you can say zoom square again, and it would look more like the answer in the book. It would look more like a semicircle. Okay. Let's do the final one here. So y equals, let's eliminate those. Notice that only one graph came up because these two were the same thing. So now we would like 1 over u minus 1. So 1 divided by. Now we want u minus 1 to be the denominator, so we'll need to be careful with our parentheses. And again, our calculator only likes to graph with input value of x. You'll notice it says y1. evaluated at x. Okay, let's go back and change our window. We want the inputs to run from -3 to 5. And our outputs to run from -4 to 4. And let's graph. And again, if we compare it to this one, you'll notice that the graph in the book gives you the asymptote there, that your calculator does not give you that. So let's look at example 3, where we're looking at a function that represents the height of a stone thrown vertically. See, the function is 30t minus 5t squared. So let's graph that. If you have a function there already, just press clear. So we would like 30. Now again, our calculator likes to use x, not t. So 30x minus 5x squared. Enter. Now we're not sure what window we're going to need, but at time t equals 0, the stone is thrown. So let's change our window. We can start at x equals 0, because remember, x represents time. I don't know how far down the road the stone will go, so we'll leave it at 10. Y represents the height here, or h in our problem, so let's change that to 0, because we'll have no negatives, negative heights. And we'll leave the y at 10. Now let's see what this looks like. So you'll notice we see it goes up, then it goes off the screen, and then it comes down. So I'm not sure how high this gets. So what we need to do is change the viewing window in the y direction. So let's experiment. How about we change the y max to 50? And see what happens. Okay, 50 was good enough. So you'll notice the stone goes up, it reaches its maximum height, and then it comes down and hits the ground again. Okay. So what are the domain and range? So for the domain, well, it starts at 0 when we throw it. And when does it hit the ground? Well, it looks like it hits the ground at 1, 2, 3, 4, 5, 6. Now, looks can be deceiving, so what we'd like to do is find out when this is actually equal to 0. So we can go back to the home screen and check to see if 6 is indeed when it hits the ground. So let's go back home. Now we have defined y1, so we can actually use y1. So we can actually type that in. So let's find our y. So y1 evaluated at 6. Let's see if that's 0. It is indeed 0. Since y1 was already defined as 30x minus 5x squared, we could use it on the home screen. Now, if the graph was a little sketchy and we couldn't tell where it actually did hit the ground, we could always solve this to find out when it is equal to 0. So we'll go back to the home screen. Solving is an algebra problem. So F2, option 1, solve. Y1 of x. We want to find out when that equals 0, comma the variable x. And enter. And at 0 and 6. 0 makes sense, that's when it's thrown, and 6 is when it hits the ground. So we have confirmation in many different ways. Okay, so let's find out how high this gets. Let's find out the range. Well, clearly the range starts at 0, because when you throw the rock it's at height 0, and when it hits the ground it's at height 0. How high does it get? We could try to count the tick marks here, but that looks fairly tedious. So how could we do that? Well, there are some things we could do. Let's go to the math menu, F5. Okay. So we can notice the option number 4 for maximum. Let's look at that. So when you're trying to find a maximum, it will try to pinpoint it for you. So it's asking you for a lower bound. So you want to get to the left of the peak. So just use the arrow keys here. Okay, I'm to the left of the peak. Press enter. Now an upper bound, so you want to get to the right of the peak. Okay, I think I'm to the right of the peak enough. And then it says, the maximum occurs when the time is 3 and the height is 45. So it looks like the range goes from 0 to 45. Now there's also a trace feature where you could try to guess. It's not as good, but if you press F3, you can see you could trace through and try to guess where it peaks. So you notice there it's 44.76, and then on the other side at 44.96, 44.99, and now it starts going down again, so we must have missed the peak. So that's not a very good way to try to figure out where the peak is. So we'll use the math menu just to refresh your memory, F5 and option 4 for minimum. I'm sorry, for maximum. Okay, well, let's check. Notice here it's solved for when it was 0. It got 0 over 6. That's what we got. And the range, 0 to 45, which is also what we got. Now again, you could have done these problems by hand, but again, part of the point of this video is to learn how to use your calculator. Okay. Let's look at the next one here, the quick check. What are the domain and range of this function? Okay. Well, let's enter our new function. So we'll get rid of the old one. So x squared plus 1 to the negative 1 power. You'll notice I'll put parentheses around the negative 1. Whenever your exponent has more than one thing, you should use parentheses. Now we'll want to graph it, and we don't really have a domain and range in mind yet. So whenever that happens, you should go back to the default window, which can be accomplished by pressing F2, which is zoom, and option 6. Zoom STD, which is zoom standard. That's the -10 to 10 in the X and Y direction window. So here comes our graph. And you can see, well, it doesn't really look like much. Okay. Notice it doesn't go very high, so we should probably change our window. Looks like it maybe goes up to 1. So let's change our window. How about we make the Y minimum and maximum -1 and 1. Let's see if that helps us. And let's graph. Alright, so it looks like the domain, it looks like it's running the whole length of the inputs along the x's. So the domain is probably all real numbers. And it looks like it goes from the x-axis up to 1. Although let's confirm that again by doing math. F5, maximum. So again, we need to get to the left of the peak and to the right of the peak. And it looks like our maximum is indeed 1. Now notice here it says that occurs when x is 1.657 times 10 to the minus 38. For all practical purposes, that is indeed 0. So it looks like the range goes from 0 to 1. Now notice, though, it comes in at 0 asymptotically. So the range would be 0 to 1, including 1, but not including 0. And let's check. Right, the domain is all real numbers. The range is 0 to 1, including 1, but not including Okay, so let's clear some things out here before we move on to the next section. By the way, if you'd like to get all this off your screen, you can use option F1 8 for clear home, and it clears your screen. And if you'd like to get rid of that, you can press clear. So let's move down to example 4, composite functions and notation. So we have f of x and g of x. So let's define those. So we've done this before. Remember, that's under other. So F4, define, option 1. So we will define again f of x to be equal to 3x squared minus x. Enter. And we will also define, now by the way, since define is already there, you could actually go in here and use the arrow keys to just change things as you need them. Right? So you can backspace and change that to G. Oops. Backspace and change that to G. And you can backspace over this and change that to 1 over x. 1 divided by x. That's another way to do entry to when you're using the same things over and over again. And enter. So simplify the following expressions. F evaluated at 5p plus 1. Okay? F evaluated at 5. Remember, p is above store. Plus 1. So notice that it is factored there. If you would like to expand that, remember that's under the algebra menu, F2, expand. Now another trick to save some typing, we could go up using the arrow keys to f of 5p plus 1, highlight it and press enter, and it will bring it down to save some typing. And there's the expanded version. How about g evaluated at 1 over x? G evaluated at 1 over x. Enter. G evaluated at 1 over x is x. That makes sense. Now we can do function composition. So f evaluated at g evaluated at x. Don't forget, have as many parentheses closing as you have opening. So 2 opening, 2 closing. And g evaluated at f of x. Now again, if you wanted to, you could just scroll through with the arrow keys, change your g to an f, and change your f to a g, and enter. So let's check. Let's check our answers here. So, looks like we have 75p squared plus 25p plus 2. Oh, that went off the screen, so let's move up to see. There it is. Next we have 3 minus x over x squared. Oh, notice we didn't get that. And again, hopefully you can see that's equivalent. So how could we get it in that form? Well, in algebra, that's called getting a common denominator. So let's go down here. That likely falls under algebra, so let's see. F2. Oh, notice there it is, option 6. Common denominator. We want a common denominator for f evaluated of g of x. So how about instead of typing that, we'll just go up and highlight it. Enter. Close the parentheses for the common denominator command. And you'll notice we get the same answer that the book does. For the final one, 1 over 3x squared minus 1. Again, we didn't get that. So we'd like to expand that. So again, F2, algebra, expand. And again, instead of typing g of f of x, we'll highlight it and enter. Close the parentheses. Well, that gave us more than we bargained for there. So perhaps we should get a common denominator and put that together. F2, common denominator, g evaluated at f of x. Enter. There we go. That gives us the answer that we were looking for. Okay. Let's go to example 5. Identify possible choices. Okay, we'll jump over that because that's not necessarily calculator based. And let's see, example 7 again is evaluating functions, so I showed you how to do that already. So let's jump down here to secant lines and the difference quotient. So the secant line is the straight line connecting 2 points on a graph. You can see the formula for it there. So let's try this out. Let's look at the examples down here. Before we do that, let's clean our screen, F18. Now that clears everything off. Now one thing it does not do is clear out your function definitions. Notice if we would type, for example, f of x, it still remembers what f of x is. If you'd like to clear all your variable names, that's under F6, cleanup. F6 is here above F1. So you would clear A to Z. That clears all your variables. So we'll say enter. See, now if we type f of x, nothing will happen. It will just say f of x because we've cleared the variable. Okay, let's clean up the screen here. Start fresh. So we have f of x is 3x squared minus x. So it's the same function before. So let's enter it again. Oops, forgot to define. F4, define f evaluated at x to be equal to 3x squared minus x. Okay, so we would like to simplify the difference quotient. So let's do the difference quotient. So we have the numerator and denominator. So be careful with your parentheses. So in the numerator we have f evaluated at x plus h. Let's find h. It seems to be above 8 there. Minus f of x. Forgot my parentheses. There we go. And that's the numerator, so we'll close that. Divided by h. Okay. And enter. And it gives us that answer. So let's check. 6x plus 6h minus 1. And let's see, why didn't we get the same answer as the book? Because the book made a typo. You'll notice here the book says h times the quantity 6x minus or plus 3h minus 1 divided by h. The h's cancel, so that should be a 3h. So it's just a typo in the book. So we did get the correct answer. Okay. Let's try it the other way. Let's do the difference quotient the other way that they mention, f of x minus f of a over x minus a. Well, now it's a new function, so we need to redefine. So f4, define f of x equal to x cubed. Okay. Now we would like to calculate f evaluated at x minus f evaluated at a. Let's see, a is above the equal sign. Now that's the entire numerator, so we'll close the parentheses. divided by the denominator is x minus a. So x minus a. Close the parentheses. And x squared plus ax plus x squared. Let's go check. X squared plus ax plus a squared. So we do get the same answer. Okay. So working through the section. Let's look at this symmetry section. An even function has the value f evaluated at negative x is equal to f of x. And an odd function, f evaluated at negative x is negative f of x. So how can we check this? Let's check if a function is even and odd. We can do it from the graph, and I'll let you read that part. But let's do it using the definition. Again, let's clean house here on our screen. So let's look at this new function, x to the fourth minus 2x squared minus 20. So we will define f of x to be x to the fourth minus 2x squared minus 20. Now, if this is going to be an even or an odd function, we should look at f evaluated at negative x. So let's do that. F evaluated at negative x. And is that the same as f evaluated at x? You can see it is. So that must be an even function. And you can tell because all the exponents are even. If we look at our function g, so let's define that one. Define g of x so that would be x cubed minus 3x plus 1. So let's check for even or odd. So we need to evaluate g of negative x. And that is not the same as negative g of x. It's not the same as g of x either. You can double check by evaluating negative g of x. Oops, I'm missing. Oh no, I do have my parentheses. Well, that wasn't very helpful, so we better use the expand. Algebra, expand, negative g of x. Don't forget to close the parentheses. So you can see g of negative x and negative g of x are not quite the same. So it is not an even or an odd function. Okay, so that was a quick run through section 1.1, but using our calculator. And again, the goal is not necessarily to learn the 1.1 material because you've probably seen it before, but the goal is to see how you can use your calculator to do these things. Okay.